Hello, everyone. Welcome to this lecture of Propulsion of Spacecraft. And the lecture of today is going to be about the foundations of propulsion. And we will talk about the main equations used in propulsion, namely the rocket equation, the thrust, and the specific impulse. Here is the outline of the lecture. So I will start by giving a brief reminder about Newton's second law. And I will derive the rocket equation, and we will see some discussion about the propellant mass versus the final mass of the rocket. And then there will be a quick bio of Tsiolkovsky, who is the guy who derived the rocket equation a century ago. And then we will talk about the thrust and the specific impulse. So I will start by giving a quick reminder of Newton's second law. And we know that by definition, the momentum of a body is the product of its mass and its velocity. So P is equal to m times v. And also by definition, the time derivative of the momentum is the sum of the forces applied to this body. So we can write dp over dt is equal to the sum of the forces. Then we can replace the expression of the momentum in the derivative, and you can write that the sum of the forces is equal to the time derivative of m times v. Then, applying the derivative rule, you can write that the time derivative of the momentum is equal to m dv dt plus v dm dt. And then there is an assumption that we generally make, which is a constant mass. So if we assume a constant mass, then this term goes to zero. And we end up with only one term, which is m dv dt, which is also ma. And therefore, we can obtain Newton's second law that states that the sum of the forces applied to a body is equal to the mass of the body times the acceleration. However, the assumption of a constant mass is not always valid. Particularly in the case of a rocket, this assumption is not valid. So for a rocket, we need to include the second term in our derivation. And this is because the mass of the rocket initially is equal to the mass of the structure, which is the mass of the nose and the shell and the fins and the nozzle and all the hardware within the rocket, which we call ms, plus the mass of the payload, which is the mass that we want to transfer to a given orbit. For example, we can want to send a spacecraft or a satellite or even humans. And then there is the mass of the propellant that is being burned and that is expelled to create the thrust that will push the rocket forward. And after all this propellant is consumed, the final mass is equal to ms plus m payload, which is the structure and the payload only. And the mass of the propellant is of the order of 90% of the total mass. So most of the mass of the rocket is propellant, and this is why we cannot assume a constant mass, because this term here is very significant. So we can also show this diagram that explains better how a rocket works here. So on the diagram on the bottom, at a given time t0, the rocket has a mass m0 and a velocity v t0. And then after short time delta t, the sum of the mass of the propellant is being expelled. And this mass, delta m, that is expelled has a momentum because it has a velocity. And this momentum of the expelled mass, that is delta m times ue, is transferred to the rocket so it can move forward. So at time t0 plus delta t, the mass of the rocket decreases by this amount, and the velocity of the rocket increases by delta v. And we can have some intuition with this thought experiment, which is called the experiment of the boat by Tsiolkovsky. So imagine a guy on a boat, and there are stones in the boat, and this person here throws the stones to the water. And each stone here has a given momentum that is the mass of the stone itself times the velocity. And this momentum is transferred to the boat so it can move forward. However, this is just a thought experiment. It cannot really work in real life because we need the stones to be really massive or the velocity to be very high. So we need the product m times v to be high enough to transfer the momentum to the boat and make it move. But this thought experiment is good enough to let you imagine how the rocket works. So, and now I will just give the definitions of the different terms that we see in this diagram. So m of t is the mass of the rocket at time t, and it depends on time. And v of t is the velocity of the rocket in the initial reference frame. And v of t also depends on time. And then you have m dot, which is the mass flow rate of the exhaust gas. And we have ue, which is the velocity of the exhaust gas relative to the rocket, ue here. And then we have v minus ue, which is the velocity of the exhaust in the initial reference frame. So this quantity is important, as we will see next. So ue is defined with respect to the rocket, and v minus e is the velocity of the exhaust gas that is observed from an external observer that is watching the rocket. So now we will try to derive the rocket equation. And for this, we need to define a control volume. So we define a control volume that encompasses both the rocket itself and the exhaust gas. And then we compute the total momentum of this control volume, which is equal to the momentum of the rocket plus the momentum of the exhaust gas. So we can write that the total momentum is equal to m times v, which is the momentum of the rocket. And this expression is pretty straightforward. And then we have this second term, which is the momentum of the exhaust gas. And the momentum of the exhaust gas is cumulative. So the longer we burn, the more momentum is imparted to the rocket. And the term here is a product of the mass flow rate of the exhaust gas, m dot, times the velocity of the exhaust gas in the initial reference frame, which is v minus ue, times dt. So m dot here is in kilograms per second. If we multiply it by dt, we're going to obtain kilograms. So the units are consistent. We have a mass times a velocity. And we do this integration between 0 and the current time t. Yeah. Then we will assume a gravity-free environment with no external forces acting on the system. So we will assume that the sum of the forces is equal to 0. And this is not the actual case in a real rocket. So in reality, we have gravity that is pulling the rocket downward toward the Earth, and we also have the air drag if we are flying in the atmosphere, and there's also the lift. However, for deriving the rocket equation, we will first assume a force-free system. And the equation that we will obtain is going to be called the ideal rocket equation. So it will give us an estimation of the mass of the propellant that we need to achieve a given mission. However, this is just an estimation because we have neglected many forces. So the actual value that we will need is going to be higher than the estimation. So now we will apply the conservation of momentum. So the derivative of the momentum with respect to time is equal to 0 because the sum of the forces is equal to 0. And then we can replace the expression of the momentum here. So we have the derivative with respect to time of mv plus the derivative with respect to time of this integral here. And the derivative of mv is just mdv dt plus vdm dt. And then the derivative of the integral is the function itself, because the derivative and the integral cancel out. So we get plus m dot times v minus ue. And we have this expression equals to 0. And then we notice that m dot, which is the mass flow rate of the exhaust gas, is equal to minus dm over dt. So dm over dt is the rate of decrease of the mass of the rocket, and m dot is the mass flow rate of the exhaust gas. And they have the same magnitude. And this minus sign is because dm dt is negative and m dot is positive. So now we will replace m dot by minus dm dt, and we will obtain this. So the two first terms are going to be mdv dt plus vdm dt. So they're the same. And then we'll get minus dm dt times v plus dm dt times ue. And then we notice that these two terms cancel out. So we will end up with only two terms equal to 0. So we will get mdv dt plus dm dt ue is equal to 0. So this is what we obtain. And then we can multiply everything by dt to get mdv plus dm ue is equal to 0. And then we can take dm ue and put it in the right-hand side of the equation. And then we can write a minus dm over m is equal to dv over ue, which we see here. And then we can integrate both sides. So we integrate dm over m between m0 and mf. And we integrate the dv over ue between v0 and vf. So we get a minus ln mf over m0 is equal to delta v over ue, with delta v is equal to vf minus v0. So then we apply the ln rule. So minus ln of x is equal to ln of 1 over x. So we invert or reverse the numerator and the denominator. So we can write ln m0 over mf is equal to delta v over ue. And then we take the exponential of both terms. So we get m0 over mf equal to exponential of delta v over ue. And then we put mf in the right-hand side. So we get the initial mass of the rocket m0 as a function of the final mass of the rocket mf, and as a function of delta v, which is the change of velocity that we want to achieve for the rocket divided by ue, which is the velocity of the exhaust gas. And this is what we call the ideal rocket equation. So as I mentioned initially, we call it ideal because we have neglected the external forces that are applied to the rocket. And there's also a quick observation here is that the necessary wet mass grows exponentially with the desired delta V. And we will see this in the next slides. So there is a very important question that is asked in rocket science, which is how much propellant MP do we need to change the velocity of the rocket by delta V? So if we prescribe delta V, which is the change of velocity that we want to achieve, how much propellant do we need? So we can write the definition of the propellant, the mass propellant, or propellant mass. So MP is just the difference between the initial mass and the final mass. and then we replace the expression of m0 by the expression found in the rocket equation. So we get this expression, and then we notice this common factor mf. So we can write mf, and we have these two terms, which is exponential delta v over ue minus 1. And this is the expression of the propellant mass versus the final mass. And we can see that it grows exponentially. So there is also an observation here, is that from an economic perspective, we want less consumption of fuel. So we want low ratio of MP over MF. In other words, we want to minimize this quantity. And we can minimize this quantity by either minimizing delta V or maximizing UE. However, delta V is prescribed by the mission. So if you want to go from a given orbit to a second orbit, then the astrodynamics of the problem will dictate to you how much delta V do you need. So you don't get to choose the delta V. However, UE here depends on the thruster. So we can imagine that to achieve a given mission with a required delta V, we can design a given thruster that can achieve a given UE. And the higher the exhaust velocity, the lower the propellant mass consumption. So the goal is to have a high value of UE. And we can observe this impact on this graph here. So this plots MP over MF, which is the ratio of the propellant mass over the final mass, as a function of the exhaust speed in kilometers per second. And we do it for three different values. The first value is 1 kilometers per second. The second value is 4.3 kilometers per second. And the third value is 5.9 kilometers per second. And the second value corresponds to a maneuver that takes the spacecraft from LEO to GEO. LEO is low Earth orbit, so the altitude is smaller than 2,000 kilometers. And GEO is geostationary orbit, so the altitude here is about 36,000 kilometers above the equator. So to go from LEO to GEO, we need to achieve this amount of delta V. And the third one is from GEO to the moon, and the moon is about 400,000 kilometers. So to go from GEO to the moon, we need this amount of delta V. And we can observe an exponential decrease. So the higher the speed of the exhaust gas, the lower propellant mass we need. So for the same exhaust speed, obviously we need more propellant to achieve the highest delta V, 5.9. And then there is 4.3 in red and 1 kilometer per second in blue. But the trend that we want to observe here is this exponential decrease. And this dashed line here represents the maximum value that is 5.5 kilometers per second, which is the maximum value for chemical propulsion. So all chemical propulsion systems operate in this range here, which is the range of very high consumption of fuel. And then electric propulsion, however, operates in this range here with exhaust speeds of the order of 50 kilometers per second. For example, the electrospray thruster, which is one type of electric propulsion, can have an exhaust speed higher than 50 kilometers per second. So if you use an electric propulsion system, your consumption will be in the lower end here. However, if you use a chemical propulsion instead, your consumption will be in the higher end here. So that is why electric propulsion is said to be more mass efficient compared to chemical propulsion. However, there is one drawback here, is that the thrust that can be developed by the electric propulsion is very small compared to the one that can be developed by chemical propulsion. So for the same delta V, if we use electric propulsion, we will have to consume less fuel, as we can see here in this figure. However, the mission time will be higher. So a mission that can be achieved in a few hours or days with chemical propulsion can be achieved in a few weeks or months with electric propulsion. So there is a compromise of mass consumption and mission time. And generally, we use hybrid propulsion, which is a combination of chemical and electric propulsion. And yeah, and now I want to give a brief bio about Tsiolkovsky, who is the person who published and derived the rocket equation. So he was a Russian rocket scientist, and he was one of the main pioneers of astronautics. And the equation, the rocket equation, was derived by him in 1897, and it was published in 1903. And one fun fact about him is that he was self-taught. He had to drop out of elementary school, and he studied everything alone. And he performed most of his work from his apartment, and he also built the Russia's first aerodynamics laboratory. And he was also inspired by the works of Jules Verne. So this is an important character in the history of rocket science. Next, I want to talk about the thrust. So let's go back to one of the equations that we derived earlier. So in our derivation, we started with dp over dt is equal to 0. And then after a few steps, we obtained this equation. And then after a few steps, we obtained the ideal rocket equation. And this intermediate equation can be used to derive the rocket equation, and it can also be used to derive the thrust equation. So we can write from here that mdv dt is equal to minus dm dt times ue. And as we showed earlier, minus dm dt is just the mass flow rate. So we can write mdv dt is equal to m dot ue. And dv dt is just the acceleration. So we have the mass of the rocket times the acceleration of the rocket is equal to the mass flow rate times ue. So, and ma is just a force. So ft is equal to m dot times ue. And this force is called the thrust. The thrust is always in the direction of motion of the rocket. And it is the force that makes the rocket move forward. So we have the gas that is expelled in this direction, and this creates a thrust in the other direction. And the expression of the thrust is equal to the mass flow rate times ue. However, this is a simplified expression of the thrust because there is a more general form of the thrust that includes the contribution of the pressure force. So if we have the nozzle here, and PE is the nozzle exit pressure, and PA is the ambient pressure. And generally, there is a difference between PE and PA. And this difference of pressure is going to create a pressure force that is equal to PE minus PA times the nozzle exit area, which is A. So now, instead of having dm dt is equal to 0, we'll have PE minus P. dm over dt is equal to PE minus PA times A, which is the pressure force. And after the same derivations that we did earlier, we will get this equation, but instead of having 0, we will have this pressure force. And from here, we can replace dm over dt by, So yeah, so we can take dm dt ue in the other side of the equation, and then we can replace minus dm dt by m dot. And we replace dv dt by a, which is, and then get ma, that is the force. So we can write that the thrust is equal to m dot ue plus the pressure force. And this is the most general form of the thrust. So there are two main contributions to the thrust. The first contribution is from the exhaust gas, from the conservation of momentum of the exhaust gas. And the second term is from the pressure force. However, in this class, we focus mostly on rockets operating in the vacuum. So PA is equal to 0. And we also focus on uh, thrusters that have a rarefied exhaust. So in this case, P exhaust is almost equal to PA. And in this case, the pressure term can be neglected, and we end up with m dot times UE. So for in-space propulsion, propulsion that happens in space, in most of the cases, we can assume a negligible pressure force compared to the uh, compared to the force induced by the conservation of momentum of the exhaust gas. So we can assume that the thrust force is equal to m dot times UE. So for the rest, we will just make this assumption, and unless it is explicitly stated that there is a pressure force, we will just use the simplified equation. And then we can define the total impulse. So if we apply the thrust to a vehicle for a given time t, we can calculate the total impulse imparted to the vehicle, which is defined as the integral of the force between time 0 and time t. So the total impulse I is equal to the integral between 0 and t of f dt, which is also equal to the integral between 0 and t of m dot ue times dt. And the objective of propulsion systems is to impart the largest possible impulse to the rocket. And from this integral expression here, uh, we can see that the longer we burn, the higher the value of the total impulse. So having a larger value of t is going to lead to a larger value of I. And having a big propellant tank is going to allow us to burn longer. So a bigger propellant tank will lead to a longer burning time, which will lead to a higher total impulse. However, we want to be able to compare between thrusters uh, without considering the size of the tank. So we want to define a performance metric that represents the capability of the thruster to deliver impulse to the rocket independently of the tank size. So to achieve this, we define the specific impulse instead of the total impulse. And the specific impulse is defined as the total impulse divided by the weight of the propellant. So ISP is the integral between 0 and t of f dt, which is the total impulse, divided by the weight of the propellant. And the thrust can be written as m dot ue. And the weight of the propellant is g times the integral between 0 and t of m dot dt. So the weight of the propellant that has been expelled since time 0 to up to time t. And then if we assume a constant mass flow rate, we can get rid of m dot here and here, and we end up with this expression here. And then under a second assumption, which is a constant exhaust velocity, we end up with this ratio, which is UE over G. So the specific impulse of a rocket or a spacecraft is defined as the ratio of the exhaust gas velocity over the gravity. And the units of the specific impulse is seconds. So UE is meters per second. The gravity is meters per second square. So ISP is in seconds. And this is an intuition that will allow you to imagine what does the ISP represent. So imagine we have two spacecrafts. One is in blue and one is in red. And the ISP of the blue spacecraft is higher than the ISP of the second spacecraft. And they have the same thrust. So since the ISP of the blue one is higher, then it will be able to achieve a higher delta V. So this blue spacecraft will consume less propellant. The mass flow rate will be smaller compared to the red one. So it can achieve, so if the thrust is the same and the size of the tank is the same, the blue one is going to achieve higher delta V. So the blue one is more mass efficient compared to the red one. So the specific impulse is a metric of mass efficiency. And generally speaking, electric propulsion have a specific impulse much higher compared to the chemical propulsion. Electric propulsion generally has a specific impulse higher than 1,000 seconds, whereas chemical propulsion has a maximum specific impulse of 500 seconds. So electric propulsion is more mass efficient. However, the chemical propulsion can have a higher thrust compared to the electric propulsion. So there is always a compromise between specific impulse and thrust that we want to make. So this is a review of all the equations we have seen so far. We have the initial mass of the rocket, that is the sum of the mass of the structure and the mass of the payload and the mass of the propellant. And there is the final mass of the rocket, that is the mass of the structure plus the mass of the payload. And we have also seen the rocket equation that gives us the initial mass of the rocket as a function of the final mass and a function of delta V and UE. So we have this exponential relationship. And we have also derived the propellant mass expression. So we have MP here as a function of the final mass, delta V and UE. And then we have derived an expression for the thrust. So this is the simplified form of the equation. We have neglected the pressure term, but the more general formulation includes a second term that represents the pressure force. And finally, we have defined the specific impulse, the ISP, as a ratio of UE over G. Thank you.